Hi everyone. Today let's talk about chapter 3. So chapter 3 is about solving linear systems. So we call in linear algebra, we learn about linear systems. So this is a linear system. We have m equations. And we have n unknowns. Okay, we can use the shorthand, the vector matrix notation. Then we get this matrix. So this matrix, we write down all of the coefficients of the different variables, and you can see we have m rows that corresponds to the m equations, and we have n columns that corresponds to the coefficients of the unknown, right? And do you remember matrix multiplication or matrix vector multiplication? We use row times column. So this guy becomes a11 times x1 plus a12 times x2 plus da 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 plus a1n times xn and equals b1. That is exactly the first equation. So far so good, everybody? Okay, and then the process of Gaussian elimination consists of the elementary row operations that transform this linear system. We can call this matrix A, okay? We can call this matrix A, and this vector be X, and then this vector is B. So A is an m by m matrix. X is an m by 1 vector, and B, okay, remember matrix multiplication, you have to make sure the inside dimension match. They're all n, right? And then the result is gonna be an m by 1 vector in this case. Okay, so elementary operation can transform the original linear system to an equivalent system, a prime x equals to b prime, which can be back solved to find x. Okay, and usually this a prime is the echelon matrix. Okay, so what are the elementary row operations? We can multiply any single row of A by a non-zero constant. We can interchange two rows of A. We can add a constant multiple of one row of A to another row. Okay, and here are the notations. Multiply row P by C. The notation is C times row P. Interchange row P and row Q. We have swap row P and row Q. Add C times row P to row Q. So we have the notation C times row P add to row Q. And you're gonna replace this new row. Okay, replace, put this new row into the row Q spot. Okay, so we replace row Q by that guy. So far so good, everybody? And then echelon matrix. What's echelon matrix? Well, it's like a matrix. We have the stair shape, right? And here we have just zeros, and here we have some number. Okay, so first, each row of E that consists entirely of zero, if there is any, lies beneath every row that contains a non-zero element. So if you have a row consists of all the zeros, is at the bottom, right? In each row of E that contains a non-zero element, the first non-zero element lies directly to the right of the first non-zero element in the preceding row, if there is a preceding row. So that creates a stair shape like that. So this non-zero must be lying on the right of the first non-zero element in the preceding row. Okay, so we get a stair shape. And then the first non-zero element in a row is called the leading entry. So in this case, leading entries are these. So far, so good, everybody? Let me just give some example. Okay, so here this is an echelon matrix. The leading entry are 1, 4, and 7. So far so good, everybody? Okay, reduced echelon matrix is an echelon matrix which we have more requirements. First, each leading entry is 1. Second, each leading entry is the only non-zero elements in its column. Okay, so the previous example, this guy is not a reduced echelon matrix. So a reduced echelon matrix should look like that. Okay, so here we have the stair shape and the leading entries are 1. And it is the only non-zero entry in its column. Okay, so this guy has no leading entry. Okay, so which means the corresponding variable is free. Okay. All right. And to solve a system of linear equations, we have 3 possibilities. We can have one solution, or no solution, or infinite many solutions. So far, so good, everybody? Okay, let's review. How do we solve this system using matrix? Okay, so first we want to write down the augmented coefficient matrix. So the first row, we have the coefficients 2, 4, minus 1, minus 1. Second row, we have 1, 3, minus 1, minus 2. Third row, we have 1, 0, 2, 2. So far, so good, everybody? So the Gaussian elimination, we want to make this guy 1 and then use it to kill the entry below it. And how to make this 1? Well, there are a lot of ways. We can divide the first row by 2, but which we won't do it because we will create fractions. We don't want fractions. It's hard to calculate, right? We want integers. So you can see the second row, we have the entries 1. The third row, we have the entries 1. So we can swap row 1 and row 2, or we can swap row 1 and row 3. Which one is easier? Looks like row 3, the numbers are easier because the 0 and then 2, 2 looks easier than the 3, minus 1, and minus 2. So there are tons of ways to solve a system. Okay, we can use different operations, but some operations are easier, some operations are harder. So I hope before you solve the problem, think about all the possible ways to solve it, and then pick the easiest and fastest way. Okay, so let's swap row 1 and row 3. Then we have 1, 0, 2, 2. 1, 3, minus 1, minus 2, and 2, 4, minus 1, minus 1. Right? And then we can use that entry to kill the entries below it. So what row operation can we do it here? We can do minus row 1 add to row 2, right? And we can do minus row 1 add to row 3. Oh, by the way, I also hope that you can try the problem first. Alright, so before we continue. Are you done? Okay, let's see. 1 minus 1, 0. 0 minus 3, 9, negative 3. 2 minus negative 1, so it's like 2 plus 1 is 3. 2 minus negative 2, so 2 plus 2, 4. 1, 2, so, let me see. Oh, we're using row 2 subtract row 1. So we should get 3, and this is minus, this is minus. Yes. So we gotta check our work. And then negative 2 R1 plus R3. So it's like we use this 2 minus 2 times 1, which is 0. 4 minus 2 times 0 is 4. Minus 1 minus 2 times 2 is minus 1 minus 4 minus 5. Minus 1 minus 2 times 2, so also minus 5. So far, so good, everybody? Alright, let's continue. Well, the next step, we want to make this guy 1 and use it to Q the entry below it. How do we make this guy 1? One way is divided by 3, but we don't want to have fractions. We want to work with integer, right? Fractions is very easy to make mistakes. So, can you realize 4 minus 3 is 1? So we can use R3 minus R2. And we usually put the rows that we want to replace in the second place here, okay? So 4 minus 3 is 1. Minus 5 minus negative 3 is like minus 5 plus 3 minus 2. Minus 5 minus negative 4 is like minus 5 plus 4. So we get minus 1. And then the last row stay there. Okay, so now we can use the 1 to Q the entry below it. So we have minus 4 row 2 add to row 3. So we have 4 minus 4, 0. Negative 5 minus 4 times negative 2. So minus 5 plus 8. 3 minus 5 minus 4 times minus 1 is minus 4 plus minus 5 plus 4 is minus 1. So the first row corresponds to x1, first column corresponds to the coefficient of x1, second column corresponds to the coefficients of x2, third column corresponds to the coefficient of x3, and the last column corresponds to the right hand side. So the last row means 3x3 equals minus 1. Well, then x3 equals minus 1/3, right? And then we can plug in the second row. Second row, we have x2 minus 2x3 equals minus 1. So x2 equals, we move the 2x3 on the other side. And what is that? x3 is minus 1/3. So this is minus 2/3 minus 1 is minus 5/3. Right? And we plug in x1 plus 2x3 equals 2. So x1 is negative 2x3 plus 2 equals, negative become positive. 2/3 plus 2. Well, the common denominator is 3. 2 is like 6/3. 6 plus 2 is 8. So we have our solution. X1 is 8/3. X2 is minus 5/3. And X3 is minus 1/3. So far, so good, everybody. So this is how we solve the system using the Gaussian elimination. Okay, next, pivot. Basic Gaussian elimination follows a specific sequence of steps and only use the operations of the form. We add a constant multiple of m of the row I to another row j. So remember the regular Gaussian elimination, we have 3 operations. We can multiply by a row by constants. We can interchange 2 rows, and we can add constant multiple of 1 row to another. But basic Gaussian elimination, we only have 1 operation. Add a constant multiple of 1 row to another. Okay, so let's look at the how does it work? Let's look at the example 2. Use basic Gaussian elimination to solve it. So you see here, to make this guy first, make this guy 1 and we don't need to make it 1. We can use this guy to Q the entry below it. We just multiply by we can subtract like a constant multiple of R1 and add it to R2 and R3. Okay, and then after we queue it, we add a constant multiple of this guy to queue the entry below it. Okay, so this is how it works. And here, let's see. So we start with, okay, 1, 2, 3, 1, 2, 6, 10, 0, 3, 14, 29, minus 7. So we use 1 to queue the entry below it. So we use minus 2R1 add to R2, minus 3R1 add to R3. So the first row stay the same. And then 2 minus 2, 0, 6 minus 2 times 2, 4. So 6 minus 4 is 2. 10 minus 2 times 3. 10 minus 6 is 4. 0 minus 2 times 1. So negative 2. And then here, 3 minus 3, 0. 14 minus 6, right? 14 minus 3 times 2 is 14 minus 6 is 8. 29 minus 3 times 3. 29 minus 9 is 20. Minus 7 minus 3 is minus 10. Right? So remember, here we only do like add a constant multiple of one row to another. Right? Here we don't like multiply a row by a number or interchange two rows. Okay, so next, use this row to queue the entries below it. And we can use minus 4R2 add to R3. Then we have 1, 2, 3, 1, 0, 2, 4, minus 2. And then here, 8 minus 8 is 0. 20 minus 4 times 4. 20 minus 16 is 4. Minus 10 minus 2 times negative 4. So minus 10 plus 8 is minus 2. So far, so good, everybody. And then this is the echelon matrix, and we are done here. Okay, and then we can get first column corresponds to coefficient of x1, and we get second column corresponds to a coefficient of x2. Third column corresponds to the coefficients of x3. Last column is the right hand side. Then we get last row. Tells us that 4x3 equals negative 2. Right? And then what is x3? Well, negative 2 over 4 is negative 1/2. Right? And then we can plug in the second row. Second row, we get 2x2 plus 4x3 equals minus 2. Well, this is the same as x2 plus 2x3 equals minus 1, right? We can divide it both sides by 2. And then x2 is moved to x3 on the other side, but it becomes minus. So minus minus become plus. 2.5 become 1. 1 minus 1. Oh! Is 0. First row, we have x1 plus 2x2 plus 3x3 equals 1. Well, x1 is then negative 2x2, negative minus 3x3, and plus 1. Well, x2 is 0. X3 minus minus become plus. So 3/2 plus 1 is 5/2. So far, so good, everybody. So our solution equals x1 is 5/2, x2 is 0, x3 is minus 1/2. Okay. And here we call, after we get to the echelon form, we call the leading coefficients, they are the pivots. Okay? Alright. So at the cave stage of the basic Gaussian elimination procedure, the appropriate multiple of the cave equations are used to eliminate the cave variables from the below equations, right? And then this element AKK is the pivot. Okay? However, finding the appropriate multiplier for each row requires dividing by the pivot elements for that stage. Okay? The process fails if the pivot element is 0. Think about it. If here, this guy is not 2, this guy is 0. What happened? You cannot use that entry to kill the 8 below it. So in that case, we need some modification, okay, which is not discussed here, but it will allow to interchange the order of the row of the augmented coefficient matrix, right? Because it's 0, you cannot use 0 to kill the entry below it. It must be a non-zero element. So we're gonna we can allow to interchange 2 rows in that case, okay? So far, so good, everybody. That is the basic Gaussian elimination. Next, I want to show you how to use MATLAB to solve a system. Okay, so suppose we have a system, and how you type a system. We use brackets, and then for a same row, we can use space or comma. But for different rows, we want to use semicolon to separate it. See, semicolon to separate it. And then after we're done, use a bracket to close it. And then we get a matrix. And then for a column vector, remember, you gotta use semicolon, don't use comma. Okay? Otherwise, the dimension won't match. So the row vector, you just put comma between them. But for a column vector, you need to put semicolon between them. And what is, how do we solve this guy? Well, here, when we solve it, it's like you multiply both sides by inverse of A from the left. And then A inverse A times A, this is just the identity matrix. Right? Identity matrix is just X when you add to it. Okay, then what does this look like? Well, this guy look like B over A, right? Do you agree? So, and you want to put the A on the left. So this is the notation for A inverse apply on the vector, add on the vector B. Okay, and you will get the answer. So this is the MATLAB. Let me actually do it here with you using Octave. Okay, so where's my Octave? Here. Okay, so actually, so in order to use the syntax or code of our course, you have to make sure the folder is, we have the M functions folder, right? But actually, when you're solving this matrix, you don't need the M functions. It's actually embedded in the MATLAB or Octave. Okay, so let's see. A equals bracket 3 space minus 1 2 semicolon. Okay, if you don't want space, you can put comma. It's the same thing as space. And 2 minus 1. Close it. You see, we get a matrix, and then B equals the column vector 7 9 5. See, we get a column vector, and then we just do A slash B. This is the solution. You can also do inverse. Okay, you can also do inverse of A times B. Okay, this will give us the same answer. So inverse of B is the inverse of B. Okay, and when you times things, don't forget to put an asterisk there. Okay, so we can also use inverse of A and then asterisk B. So far, so inverse. Okay, so far so good, everybody. Alright, how do we get reduced echelon form? So suppose we have a matrix and we can just do RREF. So that is the reduced row echelon form. Okay? So this row is for row echelon form. So that you see a double R there. So far so good, everybody? Let me do it here. Okay, so if we do, can you see it? If we do reduce echelon form of A, we actually get the identity matrix because A has a unit solution. The system AX equals B has a unit solution. Is equivalent to say the determinant is non-zero. Is equivalent to say A is row equivalent to the identity matrix. Right? Okay. And inverse of A, we just see that's IMV of A. That's the inverse. If we do it here, we can do inverse of A. So this is the inverse. You can also change the preference so you get fractions instead of decimals. Okay? Matrix operations. So suppose we have two matrix A and B. We just do A asterisk B. And then we can get the modification. And if we get A slash B, it means, well, this is the same as, okay, think about it. This is like B is on top of A, right? So this is like A inverse B. So far, so good, everybody? So it's the same as you use inverse of A times B. Okay. And here, A prime is actually the transpose. Okay, the transpose, usually we use AT to denote, but in MATLAB, we use A prime for the transpose. So this guy is the transpose of A times B. So far, so good, everybody? Okay, we can also check right here. So you know A, right? We can type A again. That's A. Then A prime, you can see, is the transpose. Right? This 2 now is right here. And negative 2 is right there. Okay? So A prime is the transpose. So far, so good, everybody? Okay. Let's continue. Determinants. So determinant of matrix, just put det of A. Right? Det of A. And let's do it here. Det of A. That's the determinant. Okay? Negative 4. So far, so good, everybody? So you can use MATLAB to check your answers. Oh, why don't we use MATLAB to check our answers? Oh, let's do that. So our first one, okay. So this is our first one, right? And let's check it. Let's see. Let me make it smaller and then make this upper. Okay. Okay, so let's call this B. So B is 2, 4, minus 1, semicolon, 1, 3, minus 1, semicolon, 1, x2 coefficient is 0, and 2. Okay, so this is the matrix, right? And the right hand side, we call it small b again. So that is minus 1, brackets, minus 1, semicolon, minus 2, semicolon, 2. We use b slash b. Okay, so the answer 2.666. This is actually 2 2/3, right? So 2 2/3 is 8/3. And then we have minus 1.66666. This is actually negative 5/3. And then this last one, minus 0.3333. This is actually minus 1/3. So far, so good, everybody. So yeah, we can use MATLAB to check our work. Oops. Alright, let's check one more. So C equals, this is 1, 2, 3, and 2. You don't want to type the entire matrix, because if you want to solve this linear system, you want to have the matrix A and the vector, the right hand side vector B, and then you want to use A/B. Okay, so 2, 6, 10, and 3, 14, 29. Close it. Okay, now our right hand side is 1, 0, minus 7, C/B. Okay. Did we make some mistake? Okay. So something wrong. So this is actually match, because 5/2 is 2.5. E to the 0 means we don't need to times anything, right? It's like 10 times 10 to the 0, so it's just 2.5. But the second one, we get 0, and this guy is like 5.32 times 10 to the minus 16. That's about 0. But why is non-zero? Maybe because in the process of Gaussian elimination, the MATLAB or Octave, they're not using exact numbers, they use decimal to compute. So that's why we have some round off error here. And then the last one, minus 5 times 10 to the minus 1 is the same as minus 1.5. So we get minus 1/2 there. So far, so good, everybody? Yes. So our answer still match. Okay, so that is the review of linear algebra and how to solve linear systems. Okay, so let's continue in video part B. See you soon!